in our paper, we study efficient competitions and online learning with strategic forecasters. So in a forecasting competition, we have competitors that are trying to predict the probability that certain events will occur. So a few examples that are commonly known are Kaggle and the Good Judgement project, among many others. After they submit their predictions, the forecasters are ranked according to how well their predictions align with the true outcomes of the events. And the forecasters' goals are to be ranked first. So a little more concretely, we have N forecasters, and they're submitting predictions over M different events. So for example, they're predicting the probability that it will rain over the next 4 days. And the competition mechanism takes their predictions and the true outcomes of the events, and it chooses a winner, which hopefully has the best predictions. So the question is, how should we pick the winner? In practice, we usually do something like a simple max of their scores. So what that means is for every event and every forecaster, we'll compute a score. So it's usually something like the quadratic score, where the closer they are to predicting the probability of the event happening, the higher their score will be. So for example, on Monday and Thursday, if they predict a higher chance of rain, they'll have a higher score. And if they predict a lower chance of rain, they'll have a lower score. And conversely, on the other 2 days when it didn't rain, the forecasters who predicted a lower chance of rain will have a higher score. And once we have these scores, we'll just add them up over all the days and choose the forecaster that had the highest one. So this is what is commonly used, but it doesn't always work in practice when forecasters are strategic. So to see this, we'll consider an example where we have 3 forecasters predicting the probability that a coin flip comes up heads. So our forecasters are A, B, and C. And here B is actually predicting the correct probability because the coin will come up heads half the time. However, using simple max, B can never win, because if the coin comes up heads, then A will have a higher score because they're closer to 0. If it comes up heads, then C will have a higher score because this is closer to 1. So B can never win under simple max. And this is something that's been noted for a while in literature. B's best response is actually to deviate to 0 or 1. Because if they get lower than forecaster A, then B will win. Or if they get higher than C, they'll win. But if they're in between, in this interval between 0.1 and 0.9, they can never win. So that's their best response, because they're not trying to maximize their score. They're trying to maximize the chance that they have the best score. And this isn't just some edge case that happens with only one event or only a small number of forecasters. We see this coming up in real competitions. So for example, in the Kaggle 2017 March Mania competition, the winner was Andrew Landgraf, and he actually explained how he modeled the distribution of predictions of the competitors and changed his own predictions to account for that in order to win. So the question is, how do we fix these skewed incentives? One possible solution in Witkowski et al. Is ELF, which they propose. And ELF works by holding a lottery over every event, and it gives the winner of that lottery 1 point. And then whichever forecaster accumulates the most points wins the whole competition. And why is that good? Well, it's good because it's truthful. So forecasters have no incentive to misreport their belief. They won't be strategic. And therefore, it's easy to analyze that ELF will actually choose a good forecaster. So they give a strong guarantee in the paper that if you use n squared log n events, so remember n is the number of forecasters, then ELF will choose a good forecaster with high probability. So that's ELF is great. It solves this problem when we have n squared log n events. But do we always have that many events? Well, let's look at that March Mania competition again. In that one, there were 442 forecasters, but just over 2,000 events. And here, n squared log n is over 1 million. And in many Kaggle and other competitions, we often see hundreds or even thousands of forecasters, but nowhere near enough events to account for this n squared log n that ELF needs. So this motivates our central question, which is, can we choose the best forecaster can we pick a forecaster with the best beliefs using fewer events? And to answer this, we showed 3 results. The first is a tighter analysis of ELF. And we showed that ELF actually can do better than n squared log n. It only needs n log n events. And secondly, we ask if we can do even better than this. And it turns out, well, we can, using multiplicative weights for forecasting competitions, we can get even better. And finally, taking our analysis of multiplicative weights and applying it to the online setting, we get the first no regret guarantee for non-myopic strategic experts. So now let's take a look at these results. We'll start with the first one, and we'll do a more careful analysis of ELF. So to analyze that, first we're going to need to introduce a little bit of notation. So let's let theta be the probability of each of the m events occurring. So this is a vector of probabilities. And each forecaster I has some belief about what those probabilities are. And we'll let that be p sub I. So a good forecaster, their beliefs will be close to the truth. Finally, or next, they each report some vector of probabilities. So in a truthful mechanism, these reports would just be their beliefs, but strategic forecasters obviously might misreport in order to improve their chances of winning. And finally, when we realize the outcomes, we get a vector y. So this is going to be some vector of binary outcomes drawn from theta, which is the true probability of the events. And then we have a scoring rule. In our paper, we use the quadratic scoring rule. The exact form doesn't matter, but what does matter is that as A and B get closer together, this will approach 1. And as A and B get further apart, it will approach 0. So using this, we can define what a forecaster's accuracy is. And this is what we use to define a good forecaster. So their accuracy is the average score of their beliefs against the true probability. So a perfect forecaster would believe exactly the truth, and they'd have an accuracy of 1. And as their accuracy drops, they'll get worse and worse. So our goal in forecasting competitions is to choose a forecaster whose beliefs are within epsilon of the best with high probability. So even ignoring strategizing, just in general, using a reduction from pack learning, we can get a lower bound for how many events we need to choose such a forecaster, an epsilon good forecaster, and that's log n over epsilon squared. So this is the best we can do, and ideally we'd achieve it, but we'll see how close we can get. So first we'll take a look at ELF again, and recall that ELF runs a lottery for each event and chooses one forecaster to award a point, and then we choose the forecaster with the most points to win. The exact form of that lottery is right here, but it doesn't actually matter for our analysis. We just need to use the fact that the probability of winning each event is between 0 and 2 over n. And as the number of forecasters gets larger, that's n, this interval gets smaller. So actually, each forecaster's total score has a pretty low variance. And using Bernstein's inequality, we can use that fact to show that ELF only needs n log n events to pick a good forecaster. And then if we consider the best case for ELF, where there's one perfect forecaster and everyone else is perfectly wrong, we can use a balls and bins analysis on the lottery to show that even in this best case, ELF still needs n log n. So that gives us a tight bound on ELF, which is that it's exactly n log n. So can we do better than that? To do that, we're going to need to design a new mechanism because ELF's lower bound is n log n here. To design this new mechanism, we'll first revisit simple max. So why are we revisiting simple max? In the non-strategic setting, where forecasters are just reporting exactly their true belief, simple max achieves the lower bound, which was log n over epsilon squared. So maybe there's some way to improve simple max slightly where we can still stay close to that lower bound. So let's look at why it didn't work to see how we could improve it. So recall that forecaster B could never win in this example, even when 0.5 was the truth. And they can never win as long as they're predicting something between 0.1 and 0.9. Their probability of winning is 0. But as soon as they report something more extreme, so as soon as they're less than 0.1 or more than 0.9, suddenly their chance of winning will be 50% depending on the coin flip. So forecaster B's chance of winning when they report, say, 0.89 is 0, but when they report 0.91, which is greater, it's only 50%. So there's a small change in their report, which is causing a big change in the distribution of the winner. So this is really a sensitivity problem where small changes in the input are causing big changes in the output. And sensitivity is something that has been studied a lot in machine learning, and we know the answer to it is regularization. So what happens when we regularize simple max? This is also something that people have done a lot. Specifically, if we regularize with negative entropy, we get multiplicative weights, which is very well known. So that's what happens when we regularize it. Multiplicative weights looks like this, where we're choosing forecasters according to this distribution pi, where that's the sum of their scores between their reports and the outcomes across all the events. And we weight it by eta and exponentiate it, and then we normalize this for all the forecasters. So as we choose larger and larger eta, this just approaches simple max. But as we choose smaller eta, we're regularizing more and it approaches uniform. So remember that ELF worked by making the forecasters truthful. So they had no incentive to misreport. So the question is, how does multiplicative weights do that? Does it prevent forecasters from strategizing? Well, it doesn't actually. No matter what eta we choose, as long as it's greater than 0. But multiplicative weights is for eta approximately truthful, which is a fact which we can use to show multiplicative weights is accurate. But first, let's look at what exactly this means. So to define approximate truthfulness formally, we need to borrow some concepts from game theory. So specifically, we're going to use dominated strategies. So what that means is if A and B are two strategies, then A dominates B if it's always better to choose A over B, no matter what any other player is doing. So there's always an incentive to choose A. So recall that for ELF, or a truthful mechanism, reporting exactly your belief was the dominant strategy. So misreporting at all will be dominated by reporting the truth. So that's what ELF guaranteed. For approximate truthfulness, we're saying that misreporting by more than gamma, for gamma approximate truthfulness, will always be strictly dominated by something in this interval. So no forecaster has an incentive to misreport by more than gamma. So the reports will always be here. And now if we go and look back at that theorem, it said that multiplicative weights was 4 eta approximately truthful. So 4 eta is our gamma here. So if we choose eta small enough, then this interval, which is 4 eta on each side, will be very small also. And that means any report that the forecasters have will also be very close to the beliefs. And when the reports are close to their beliefs, our analysis of multiplicative weights starts looking very close to the simple max non-strategic one. So we can show that multiplicative weights is still accurate. Specifically, if we choose eta on the order epsilon, then we know that multiplicative weights will choose an epsilon accurate forecaster with high probability if our number of events is on the order log n over epsilon squared. So this is the exact lower bound we talked about before. So this is the best we can do, which is pretty exciting. That multiplicative weights is actually optimal up to constants in this case. And the proof follows by using the Hofting bound combined with approximate truthfulness. And yeah, this matches the best. So that is basically the best we can do in this situation. So let's now, instead of looking at this problem, we'll look at a different problem and see what we learned there. So we'll look at a whole new setting, which is online learning. So completely different problem. But here we have online learning from experts. So we have a series of rounds from 1 through T. And on each round, the experts give us some advice. And our algorithm will choose choose the advice of one of them and use that as its prediction. And the goal of the algorithm is to be almost as good as the best expert's advice. So this is the standard online learning from experts situation. But now what happens when the experts have some stake in the algorithm's prediction, specifically if their goal is to be chosen? Will they still report truthfully? Will their advice still be good? Well, we don't actually know. So let's try and analyze that. So we're still in the same situation where we're getting advice on rounds 1 through T. And at each round, we're still going to choose one of their predictions and use that, choose their advice and use that as our prediction. But here, the expert's goal, since they're strategic now, their goal is to maximize their chance of being chosen in the final round. So that's all they care about. So to account for that, they might misreport. So now we have to account for their beliefs P, which may not be equal to their reports R, since they're strategic. And the algorithm's goal, instead of being as good as the best expert's advice, now we want to be as good as the best expert's belief, which is a little bit stronger because we don't actually know their beliefs, only their advice. So the question is there such an algorithm for strategic experts? The myopic case has been studied previously, and there are results that there are known results here when the experts only look one round ahead, so they just care about being chosen in the next round. But in the non-myopic case, this is still an open question. But it turns out using our analysis of multiplicative weights, we can show that it's actually no regret in this situation. So such an algorithm does exist, and it is multiplicative weights. And notably, this is no regret with respect to the expert's beliefs, not just their reports, which is the standard notion of regret. So this is even stronger. We show that multiplicative weights is no regret with strategic experts. And that follows from the standard regret guarantee and approximate truthfulness. So to recap, we first did a tighter analysis of ELF, showed that it was exactly n log n, order n log n events. And then we looked at a better algorithm, which was multiplicative weights for forecasting competitions. And we showed that it was for eta approximately truthful. And that lets us show that it's accurate with order log n over epsilon squared events, which is optimal. And finally, we looked at multiplicative weights for online learning from strategic experts. And we gave the first no regret guarantee for non-myopic experts. Thank you.